Good day, everyone, and thank you so much for attending this webinar today morning. My name is Murli, one of the core member of Purple Synapse with a few years of cybersecurity experience. Uh, Purple Synapse, located in Bengaluru, which is our world-class cybersecurity research, innovation, and attack simulation labs, also provides the red and blue teaming skills and trainings. So in order to secure the information systems of our customers, so we provide all this cyber range and purple range labs for the training modules. So this webinar is happening in association with KTech. KTech is Cybersecurity Center of Excellence, really a good initiative from Karnataka government to spread cybersecurity awareness and innovations. So as you guys know, this webinar is all about providing you basic awareness of buffer overflow attack. So the guy who is sitting next to me is Sai Kailash, is going to present you with this webinar. And about Sai Kailash is one of the security researcher and certified ethical hacker and a penetration tester. So Sai Kailash, welcome to this webinar. And yeah, you can take the control for now. Thank you.
Hello. Yeah, good morning, everyone. Hope you're having a great morning and hope you had some breakfast for this session so that we can start off. So, should I be waiting for a couple of minutes or should I start? Like,
You can go ahead.
okay, so I'll be starting off. Just it'd be great if you guys can ping me in the group chat if you can, if I'm really audible or if I need to alter my tone in any way. Anyone? The rest of you guys, if it's fine, you can just go ahead and ping me in the group chat. If that'd be great, so that I am sure that everyone can hear me and I can continue with this tone. Okay, thank you. Great. So let's get started. So I'll be basically giving a basic concept. Like I'll be explaining the basic concept of stack-based buffer overflows. So what can you expect from this webinar? You can expect a basic cybersecurity awareness as to how buffer overflow attacks are exploited in real, how the concept of stack-based buffer overflows, using stack-based buffer overflows for saved return pointer override exploitation. This I'll be explaining more in detail as we go through the practical demonstration in the webinar, and an introduction into the world of exploit development. So how basically how we start off the journey of exploit development. I'll be sharing with you few of the steps as to how exploit development actually goes about in various phases, from the initial exploit to an exploit that we can fire and get the shell directly. A small disclaimer: this webinar does not cover the concepts of modern compile time protections like DEP, ASLR, or stack canaries. These are modern compile time protections that make exploit development tricky in a way, and we'll have to party like it's the early 2000s to get this to learn the basic concept first, and then we can move ahead. Okay, so what is a buffer overflow? A buffer overflow occurs basically in a situation where a program or a process, it can be an executable, an application, attempts to write more data to a fixed length block of memory. So we have a fixed length block of memory, and a program or a process tries to write more data than the memory allocated to it. That's when the buffer overflow happens. So an example of data stored in buffers are login credentials or the host name for an FTP server. For example, when a username with a maximum of 8 bytes is expected, but a username of 10 bytes is given, and the buff and is written to the buffer. In this case, the buffer is exceeded by 2 bytes, and an overflow will occur when it's not prevented from occurring. So what can an attacker do in this situation? An attacker can leverage this to craft to craft an input to an application, which can cause the application to execute arbitrary code. This can also lead to the compromise of the machine if arbitrary code is executed. What are the impacts of a buffer overflow attack? It can lead to, like I said, remote code execution. It can lead to privilege escalation in a bad situation, and it can also lead to denial of service in other ways. Why does a buffer overflow attack occur? So this can happen due to bad programming from the developers of the application, and also can happen due to poor input sanitization given to the application. These are the few reasons why a buffer overflow can occur. Uh, so let's move on to the next slide. So what are the, I'll be showing you a practical demonstration of a buffer overflow after this mini small presentation that I have put together. What you'll be needing is the target we'll be trying to exploit is minishare 1.4.1. It's a free float FTP server that is running on HTTP port 80 that allows us to upload files or download files from the server, and is a basic FTP server running on port 80. The tools that we'll need is any Windows operating system will do for this demonstration, because we are disabling DEP and ASLR in any case. So any Windows operating system should do the trick. Along with that, we'll need immunity debugger. This is a debugger to which we attach the executable to study it in memory. Sorry. And we'll need a plugin called mona.py, which is built by the Coreland team and is available on GitHub. This is a script that will help us locate few instructions within the executable that I'll be discussing more in detail through the practical demonstration. And any flavor of GNU Linux will be good for this. Will be good to perform this attack, like the scripting and the exploitation part, along with the Metasploit framework. So I know. So let's move on. Here we have the immunity debugger interface, which we'll be seeing a lot through the practical demonstration. So I thought it'd be great if you guys get comfortable with the interface at first. So at the top here, we have the execution controls. This allows the whichever process we attach to it, it allows the process to be restarted, closed, run, or paused. And also it allows to navigate using this button here. We can navigate to a particular memory address. Okay, so this is the dissembler section, which is the main CPU section and is important. It shows the contents of a binary file as assembly instructions, as we can see here. The next instruction to be executed by the CPU is always highlighted. As we can see, this instruction is highlighted as it's the next one to be executed by the CPU. This is the register section, which shows the current state of the CPU registers. The most important ones being EAX through EIP, which are always present at the top of the pane. The next area is the dump, which is this lower left-hand side section. The dump shows the contents of the process's memory space as a binary dump, basically your ones and zeros, and can be useful for examining regions of memory. This can be very useful for examining the regions of memory to see if we write anything like any shellcode to this memory, how it looks in the memory. This is the stack area, which shows the current state of the stack, with the top of the stack highlighted always. This, as you can see, the top of the stack is always highlighted, and this is when we push something onto the stack, it keeps growing in this direction, and the top of the stack is highlighted. and the stack goes downward in this case. The command input, which is this area here, um, is used to basically interact with Immunity Debugger and its plugins like Mona.py in a command-driven fashion, basically like your Linux or Windows terminal. As it's the same thing, but you use this to interact with Immunity. The status bar shown down, which shows the various status messages. Like if we crash this application using our script, the exception or will be raised here, and the status will be shown here, and the process state, basically your bottom right, which is at the corner. This shows whether the process is basically in a running state or in a pause state. So let's move on to the next slide. Okay. So these are the various phases of buffer overflow that I'll be demonstrating through the practical demonstration. I'll be going through each of these in detail and will be explaining to you from how we built the basic skeleton code to crash the application. I'll be going till the point where we exploit and gain full control of the target system. So I'll be going through the full phase in detail. So let's jump on to the practical demonstration. So I'll be basically showing this practical demonstration on VMware, where I have a Kali Linux machine and a Windows machine. This Windows machine can be of any operating system from your 7 to anything. You just need to have dep and ASLR disabled for this. So I'll just jump on. Okay, so this is basically my Kali Linux interface that I'll be using for this practical demonstration. The IP of the Kali Linux machine, as I'll be showing here, is 192.168.100.11, and the target machine, which is a Windows machine, I'll be showing the IP of this is 192.168.100.12, and we can, as we can see, using the netstat command, minishare, which is the vulnerable executable, is running on port 80. As I've run the netstat command, and we can see here it's running on port 80. So let's go ahead. Okay, so basically the first question we need to ask ourselves is, how are the bugs found in applications? So how are these vulnerabilities discovered in the first place to go ahead with? So there are three main ways of identifying the bugs in applications. The first way is when you have the source code of the application. When you have the source code review is the easiest way to identifying bugs, by identifying the coding errors in the source. So that will come in the first position. The second way is, if the application is closed source, we will have to apply reverse engineering to find these bugs. Third way is, applications have input points. So basically, we first identify the input points, send malformed data to these input points, and observe unexpected behavior of the application. This process, like this process of sending malformed data to the input points and observing the unexpected behavior of the application, is called fuzzing. The unexpected behavior shows the application is not filtering any inputs correctly and may be vulnerable to like a buffer overflow vulnerability. Okay, so we will look at an example of a simplified fuzzing scenario that will exploit a buffer overflow vulnerability on Minishare version 1.4.1, which is a free float FTP server. The webinar will cover the steps to exploit the buffer overflow vulnerability in the HTTP GET request for Minishare 1.4.1. So I'll go ahead and show you the fuzzing script that I have written. And also a point to note, not only the get method is vulnerable to the buffer overflow for minishared 1.4.1, the head and post methods are also vulnerable. The difference is minimal, though both are exploited in almost the same way. So you can go ahead and experiment with that as well. Um, so the vulnerability lies when an attacker can send an overly long get HTTP request through which he can gain control of the target system. So we will now look at this Python script that will fuzz the get request for us. The script starts with by importing the network socket module, which is present in this line. And the script also shows these lines, which are responsible for creating a buffer array with increasing buffer sizes. So these lines create a buffer array of increasing buffer sizes, which will be part of the HTTP GET request. So basically, what's the result of this script? Uh, yeah. So the result is that a script is the script repeatedly connects to the minishare FTP server, attempting to send growing lengths of buffers as the HTTP GET request, which will cause the vulnerable application to crash at any point. So you can go ahead and like just I'll show it to you once again. So this is the basic script that the skeleton script that we'll be changing and throughout this demonstration. Yeah, the script has been developed by me. It's a very basic Python script. It's very easy to use, and it can be easily changed for demonstration of this buffer overflow vulnerability. Okay, let's go ahead. So now that the minishare 1.4.1 fuzzer is ready, let us examine, let us run it actually against the minishare instance. I'll start by making sure that the minishare instance is up and running, and we can also start the debugger and make sure that the running process is attached to it. So here I'll just start it up, and I will start the immunity debugger as well, and I'll make sure that the running process is attached to it. This is the simple step. You can go to File, Attach, find your minishared instance, which is located right here as I've highlighted on the screen, and we can just press the attach button and it'll open up in memory like the various when we attach a process to immunity, it first is in the pause state. So we need to press the play button here to release it and get it in a running state. And also to improve the font set, we can right click at any part that where we want to include it, improve it, and go to appearance here, present here, and the font. So basically I've kept it in this format so that it is visible for everyone so that they can see clearly. And also you can change the font of the dump by right clicking the same way and going to font, and I've kept it at the same format so it's visible for everyone. So let's go ahead. So now that the debug process I put it in a running state. So now that the debug process is up and ready to go, we can run this fuzzer against this process. So I'll be using the command python fuzzer.py and press enter. So as we can see, the fuzzer sends larger and larger GET requests, which increases by 100 bytes each time to the minishare server on each try. And until, so it keeps sending large requests until a buffer length of around 1,800 characters long. we will see that when it reaches 1800, what exactly happens. So you'll have guys have to wait for like around 30 seconds. They should be good to go. So it's just sending, it's fuzzing and sending get requests with a longer get request each time to see if this, like, so basically we are trying to observe the unexpected behavior from the application. That's when we know if it's like vulnerable to a basic vulnerability. So it's still fuzzing. And so until we reach a buffer length of around 1800 characters long, immunity should end here. So immunity pauses, like as we've pauses, and says that the debug program has raised an exception. So it's raised an exception when executing 41, 41, 41, which is A in hexadecimal, which is basically capital A's in hexadecimal. Uh, as we can see that the registers, like the registers here, contain the user supplied input, which I basically in my fuzzing script, which I'll be showing you now, I've supplied capital A's in a fuzzing script. So it overrides the extended instruction pointer. It overrides the ESP. As we can see, we can follow this and see that it's been overwritten with capital A's, and also the EBX has also been written with capital A's. So just show it to you once. So you can see that it gives the error message saying that the server crashed with a buffer length of 1800 characters long. And if we see the fuzzer again, we can see that we have sent multiple 41s, which is basically capital A in hexadecimal. 41 is capital A in hexadecimal. And we can see that it has overwritten almost the EIP, the ESP, and the EBX. So an important point to note here is that the EIP controls the execution flow of the application, and we might be able to divert the execution flow to a place of our liking, such as a place in memory where we can introduce our own code. See, the EIP has been overwritten by the 41s that we have supplied as user input. So if we manage to craft a buffer carefully and embed some malicious code in it, we can have the program redirect this execution towards this embedded code and execute the code of our choice. Let's see how we can proceed from here towards developing an exploit for this vulnerability. So let's close the debugger here and restart the minishare service. We restarted it, and let's go to immunity and just get acquainted with this step of attaching the minishare process to the immunity debugger. So it's right here. We press attach, and again we can see it's in a pause state, so we play it. Yeah, so let's go back. So the fuzzer that discovered that the minishare version 1.4.1 get HTTP request buffer overflow vulnerability, and we have seen that the get request of around 1800 bytes creates this buffer overflow as highlighted earlier. Allowing this get request basically corrupts the memory, and we can also gain execution control of the minishare program. The first task of exploit development is to write a simple script that will replicate this crash without having to run the fuzzer each time. So we don't have to keep running the increasing HTTP GET requests. We can just write a fuzzer that will replicate this crash. This script will allow us to make changes in the skeleton script and observe them with more ease in the debugger. This script creates this script creates a buffer of 1800 A's, which I'll be showing you. I'm just going to be putting more A's in for the sake of padding. So yeah. So this will be the script that will replicate my crash. Um, and I'll send it to the Minishare FTP server as a GET request. Let's attach the Minishare executable, which I think I've done that already, and I will be I will be sending the script as a GET request and see if it replicates the crash. So I'm going to be running the script using the same pipe. Let me just get that script. One second. Okay, so Python, the script name. Um, 192.168. This is the IP address of the Windows machine, which and the Minishare executable, which is running on port 80. So we can see on running this script, we can see it's given us an error message saying it's crashed. And on going to the immunity debugger, again, we can see that the EIP has been overwritten with 41s, and also the EBX and the ESP has been written with capital A's as well. Considering that the EIP register controls the execution flow of a program, getting control of this register is highlighted is an important aspect of exploit development. A cycle as these 4 bytes of the A's in the fuzzer that we sent around 2,200 A's. These 4 bytes, which I've highlighted, end up overwriting the EIP register. So it is vital to locate the position of these 4 A's in the buffer. So out of the 2,200 A's that I've sent, seeing the program here, 2,200 A's that I've sent, it is vital to locate the position of these particular 4 A's that override the EIP, as the EIP controls the execution flow of the program. So an easy method of identifying the position of these 4 bytes is to send a unique string of like around 2,200 bytes, like um, uh, rather than just A's, we can send a unique string of 2,200 bytes. Then we note the 4 bytes that write the EIP and locate the position of these bytes in the unique string. So I'll close this again and go through the same process of starting it and attaching it. So how do we create this unique string? So we have a utility, a useful utility for generating such unique strings. In is a tool called the Ruby pattern create tool, which is located in this. If you want to note it down, user share metasploit framework tools pattern create.rb. Okay, so user share metasploit framework tools pattern create.rb, and we want a length of around 2,200, or we can keep it at 1,800 if you like. So here, just hold on for a second. I'll just pause it for 1 second. Just going through that directory. You pause. Is it paused? 1 second. Okay, we just search for it manually. I'll just be pausing it for a second here. Yeah, just give me a minute. Okay, you can start again. Okay, guys. Okay, sorry for that. I'll be continuing. Next, I have a small part here that I should have included. So there is user share, Metasploit framework tools, exploit pattern create, and we'll be creating a pattern length of around 1,800. So I'll just, I don't know why this is not working. Oh, come on, this should be uh, exploit. Oh, well, so sorry for being slow. S- s- Okay, irrespective of any problems that I'd encountered, I'd already created this unique pattern, and I'll be showing that to you right now. So you can see Nano, and I'll be opening up the script here. So using that using that tool that I'll be showing you in a minute. Yeah, it's right here. The user share Metasploit Metasploit framework tools exploit pattern create. Okay, so sorry, my bad. Was doing a small error in that. I was putting hyphen instead of an underscore. So here goes. So you can see that this will create a unique string with none of the 4 bytes being the same as the previous 4 bytes, which will help us identify the string, which will help us identify which 4 bytes exactly override the EIP. So here you can see it's created a unique string with none of the 4 bytes being similar to each other. So I'll be showing that to you in a script which I have put in here. So this is the script. You can go through it, and it's basically just included in the buffer, the GET request, the buffer, and the HTTP request, and the same connection as we go ahead. So I'll be sending this using Python again, Python EIP cater, and 192.168.100.12 port 80. So I'll just confirm that this is running. Okay, it is. And yeah, it's crashed again. And we can see that an exception is again raised. And the EIP is overwritten with exactly these 4 bytes. As we can see, these 4 unique bytes, as we can see. Yeah. So we'll use these 4 bytes. Just give me a minute. Give me 1 second. I'll just continue. Yeah. So we have these 4 bytes that we'll use, and so how do we identify which exactly are these 4 bytes that we sent in the unique buffer that is going to override the buffer that we want? So we'll copy these 4 bytes, 43366 843, 43366 843, and we'll write it down here. 43366 843. Okay, so we'll use So, and now that we discovered the unique 4 bytes in the buffer that override the EIP, we just need to find them in our unique buffer. So we use the companion tool for offset create, which is of pattern offset, to discover the exact position of these bytes. These 4 bytes are located at an offset of, so we use the tool like this, so to discover where these 4 bytes are exactly located. This one, we'll the original length that we sent, q, and we will paste this address in. Mind you that this address is the exact one that has overwritten the immunity, as we can see. And on pressing enter, we see that these 4 bytes are located at an offset of 1000 1788. Let's use this information to form a new modified buffer string and see if we can control the EIP register using the skeleton exploit. So I've written this code as well. So it's called EIP validator. So we send the A's. So basically, the buffer is modified to reach 1788 A's, which will reach the location in the buffer which overrides the EIP, and the 4 B's, which will be the bytes that override the EIP itself. So we should be expecting 42 4 times, which is hexadecimal for capital B, overwriting the EIP, and then pad the rest of the buffer with C's. So let's run it. Just change this, and we have to go through the motion of restarting this again and attaching the process to it, because it crashes each time we send our overly long get request. So here goes. And release it, and once we run this, we again see a crash, and on going to the EIP register, we can clearly see that it raises an exception and has been overwritten by the clearly overwritten by the 4 B's, showing that the calculation that we made was correct. We can now control the execution flow of the Minishare program by changing these the ones highlighted, by changing these 4 particular bytes. So now let's go to the next phase, which is shellcode creation. So now how do we redirect the execution flow now that we can control the EIP register? Part of our buffer can contain user introduced code or shell code that we would like to have executed by the Minishare application. Once this shell code is in memory, we can redirect the execution flow of the Minishare program to the shell code. The next steps that I'll be demonstrating will involve examining and preparing space for this shell code and figuring out a way to redirect code execution to it. We can follow as we can see, this has been overwritten by C's, which is the next part as I showed right here. Okay. See, we have the B's which override the EIP and the C's following it. And here we can see. So if we follow the ESP register in dump, which just say follow dump, the dump and dump the memory at that location, which is this address, we can see at the time of the crash, ESP points to this address, which ends up somewhere towards the end of our buffer. Just as the capital C's in hex starts. So basically, there are C's, sorry. These are the C's, and these are the contents that the content that the ESP register is pointing to. This happens to be the same exact spot where the capital C's begin. So the B's end, which is contained in EIP, and the capital C's begin at the same exact spot, which we should consider as a convenient location to place shellcode, as it is easily accessible through us through the ESP register later on. So I'll be explaining a little short thing which I'll need for my video here. I need my presentation here again. So bad characters, depending on the vulnerability type, application, and protocol in use, there may be certain characters that are considered bad and should not be used in the buffer, return address, or shellcode. An experienced exploit writer like knows how to check for any and all bad characters before continuing the exploitation process. So an easy way to do this is by sending all possible characters from 00 to FF, which in hex, as part of the buffer, and seeing how these characters are to be dealt with when the crash occurs. So these are the, due to this time constraint that we have here, I've already done this process and filtered out the 3 characters that shouldn't be sent, which include the null byte, which is used to terminate a string copy operation. So when we are especially sending strings of A's, B, and C's, we when the CPU encounters like a null byte in memory, it would truncate the buffer to the point where the first null byte appears. So the rest of the buffer would be neglected if a null byte is present in our buffer, return address, or shellcode. The carriage return, which is 0D, a carriage return signifies that the application, like the end of a particular field. So basically, if we send a HTTP GET request, and in the GET request, it consists of 0D in hexadecimal, it would terminate the GET request at that point. So anything further after the 0D wouldn't be considered. So we basically can't send this because the shellcode might be truncated, the return address might be like hampered with, or our buffer itself might be might get mangled due to the presence of this a carriage return. The line feed character is basically the same as the carriage return, which signifies to the application that the particular field has reached its end and it should neglect everything further. So I'll be going ahead with the next phase after this, which is discovering the space in memory. So we've already discovered the space in memory, which is the ESP register. So let's go ahead with this. The next phase, which is finding the jump ESP instruction. Just hold on 1 second. Yeah. Let's go. Make this full screen, and yeah, start. So redirecting execution. So we found the place for the shellcode in the memory location. Like as we see, I'll just show it to you again, so we'll refresh our mind. That is accessible through the ESP register. We control the EIP registers as it has been overwritten with the B's. We figured out what characters are allowed to be in the buffer and what not, as I just showed you the bad characters list that we've made. The next task is to redirect the execution flow at the time of the crash to the shellcode. So we'll place a shellcode exactly at this location here to the memory address. ESP is pointing to. The most intuitive way of finding this memory address is to replace the B's with the address that pops up at the ESP register. So we can basically replace these 42s with this memory address located here. But this won't sadly work, as stack addresses change often, especially in threaded applications such as Minishare, where each thread has its own reserved stack memory allocated by the operating system. So it's not possible to hard code this address to these 44s. When an application runs, it is first mapped into the memory together. So how do we do this? So how do we basically find the address that makes EIP execute the next instruction that points here where we'll be placing our shellcode. A more generic way to find a place that the ESP points to at the time of the crash is to use like DLLs. So what are they? So when an application runs, it is first mapped into memory together with any DLLs, drivers, modules it may require. These modules contains basically extra functions and data that the program needs in order to run. We can therefore look for naturally occurring instructions. So basically, we can fill this space with a naturally occurring instruction such as jump ESP. So when it crashes, EIP points to the memory address present in ESP, which in turn contains the shell code that will give us arbitrary code execution and control of this target machine. So we can find naturally occurring instructions such as jump ESP in these modules loaded. We can jump to these addresses of these instructions instead, which will have the like basic effect of redirecting the execution flow of EIP to whatever address present here at the time like here, which contains a shellcode. Thus, the shellcode executes. To quickly get an idea of how these DLLs and modules are mapped in memory, we can use a useful third-party immunity debugger script called Mona, which I've mentioned earlier, created by the Corelland team. The script is already installed in the debugger, so I will type Mona modules. Yeah, modules and an extensive list from here to here. We get an extensive list of all the modules that of the debug application is like whatever extensive list is displayed. We will now need to choose our instruction from a module that matches a few criteria. So basically, as I mentioned earlier, that depth ASLR should be disabled. So the so that yeah, and also the address that the jump instruction has should not contain any bad characters. So the module that suits this criteria is basically this one, the shell 32 module. This DLL does not have any memory protection mechanism enabled. This makes the exploitation process fairly straightforward, as we do not have to deal with the bypass mechanisms, as this is a basic exploit development. So now that we found the mini shell 32 DLL, we will have to reliably load at the same address, which this DLL loads at the same address on each reboot. So we need to find a naturally occurring jump ESP instruction and find at what address this is located at. So for that, we can use a command in Mona, this inbuilt, called Mona JMP for the jump, the register that we are focusing at ESP, and the module that we are going to use, which is dash M shell 32, sorry, shell 32 dot DLL. Need to put this down and sorry. So here we go. So we have we have seen this particular instruction, which consists of 7C, 9D, 30 and D7, which is a jump ESP instruction present in the shell 32 DLL that we can use to override the EIP register that will point it to the shellcode that we are going to place. So let's restart and see 7C, 9D, 30, D7. So this is the address jump ESP that we are going to use, and I'll go through it of starting again. And fine. Attach, initialize. here it is, and attach it. I'll go back and run this. Okay, so so we can see this. You can write the code for this by using nano jump ESP, and you can already see that I have already hard coded this address, but I have, you can see that 7C D9 319F has been written in reverse, as this is x86 architecture, and it is expressed in Little Indian format, so it's written in.
So in the final step of this buffer overflow demonstration, we'll be first building the payload that is going to be included in our exploit using the MSF Venom command tool. So here I've shown the MSF Venom command to build the payload using a TCP reverse shell for Windows, specifying the listening IP address, the local IP address on which we will which is the IP address of this machine, the attacker machine, the local port on which we'll be receiving the shell, which is 4444. The format of the payload, which will be in Python, as the original exploit code is written in Python. As I mentioned, the bad characters that we are supposed to ignore, leave out while building the exploit, the architecture, which is x86, while the platform it is for, which is Windows, as the target machine is of the Windows operating system, and the number of iterations. So once we press enter for this, MSF Venom uses these parameters to build a payload, as we can see shortly. Just give me a minute. So once the shellcode has been built, we copy this and paste it into our original exploit, as we can see here. We paste it, as I've already done it, we do not need to do it again. We then go to our Windows system, make sure that minishare has been started, like we can see here. As it's already been started, we can go ahead and fire the exploit and get a reverse shell of the Windows operating system, as we can see here. Also to note that I've already started the netcat listener on port 4444. So when we exploit the Windows machine with minishare 1.4.1 running on it, we will get a shell of the same. And as minishare is running on port 80, we specify the port and run it against the system. As you can see, the system is successfully exploited and we get a reverse shell from the Windows machine. I will confirm this by checking the IP address of the Windows machine, and here you can see we have successfully exploited the Windows machine, and due to the by leveraging the buffer overflow vulnerability present in minishare version 1.4.1. So thank you. I'll be taking whatever questions you have for me right now, so you can go ahead.
Going through. Can you just post the question in the chat? How can we find the bug overflows in the exe? There are three ways to doing this. Basically, you can use you can if the application code is open source, you can basically review the application like open source code, find the bugs in it. If it's closed source, it's probably very hard to find the bug, but you'll have to reverse engineer. And what most attackers do in real time is basically send increase like find the input points to the application and keep sending various input points of varying length. And once you find keep sending varying length input points, you can observe the unexpected behavior from these application which cause it to crash. Yeah, so that's basically you find how you find these bugs in the exes. Any other questions? Sources to learn this, you can SL Mail 5.5 is the very basic one for Windows. Most of the people who teach buffer overflows use SL Mail version 5.5. And also a very good tutorial that you'll find on the net is uh, with do stack overflow good. I'll just be typing that. It's do stack overflow stack buffer overflow good by Justin. He is actually his resource is really helpful in learning stack overflow, as he's given a very beautiful and in-depth tutorial as to how to learn stack overflows. And yeah, you can definitely do it with ASLR and dep enabled. That wouldn't be a 1 hour webinar, then it would be pretty long, as it's a it's like we were just doing this to step our foot in expert development, and this is a long the one with ASLR and dep enabled is the tricky of ones, which you need a little bit of experience with exploit development for it to actually work. Sure, you can just mail me at my email address, and I'll be sending you the recording of the webinar. Any more questions? Anyone else? If you have anything, that'd be great. Any more questions? Anyone? So that I can answer them. Okay, if there are no more, what if we cannot insert padding? You can always find spaces in memory that not necessarily be ESP. In situations, you can just make it jump to another location in memory. So what you'll have to do is observe the registers carefully. So what I'm trying to say is, I'll just show it to you. You'll have to observe the registers carefully. Once you observe these registers carefully, you'll be any of these registers, follow them in dump, see how your code is overwritten with the C's or the A's that you send, and then you can see where exactly you can place it. So you can find you don't need to exert like put padding necessarily, but you can find other registers where you will find open space to place your shellcode. Any other questions? No, this is a stageless shellcode that I have used. It's a basic reverse shell without any stager in it. It's a stageless shellcode that I'm sending. Any other questions? Okay, so if you guys have no more questions, I'll be ending this share. Thank you for sparing your time for this webinar. It was a great experience showing you guys. You can encode the shellcode using Shikata Kanai. It's MSF Venom -E option. Just type -E, and you can use any of the encoders available with the MSFNM that are default. It has plenty of them. You can study each one which suits your situation and you can use it. Okay, so I'll be ending this webinar. Thank you for your time. Uh, thank you, Deepak Kumar. It was great showing this webinar as well. Thank you. It was great. So hopefully we'll do more webinars with advanced topics. Thank you. See you guys. I'll be ending the share right now. Thank you.
So in this video, I'll be showing you how to leverage the buffer overflow vulnerability in SLMail version 5.5.0 on a Windows 7 machine. So let's start. So this is the IP of my attacker machine, which we'll be using to exploit the Windows 7 machine, which has SLMail installed on it, which is a POP3 server running on port 110. In this video, I'll be showing the final step as to how to construct the payload and how to put it in the final exploit and use it against the SLMail server. I will not be showing all the steps covered in the webinar as they are almost identical, except identifying the bad characters and also choosing the return address. The return address is different for each operating system and has to be chosen carefully. So let's start. I'll make sure that the SLMail server has been started. As you can see in this, it has been started, and I will also make sure that SLMail is running on port 110. As you guys can see here, SLMail is running on port 110, and also I will show you the IP address of this Windows 7 machine below. It's 131. So I will use this exploit as shown, which is an exploit for SLMail 5.5.0 server. It consists of the payload that we have created using the following options. MSF Venom is used to create the payload, which is a reverse shell payload for Windows, the local attacking machine through which we will launch the exploit, the port on which we will get the shell of the target system, the bad characters to be avoided, and the format of the payload is in Python as the exploit itself is written in Python. The exploit consists of a buffer of 2606 A's along with the return address for the Windows 7 machine, which is shown here. Then it consists of 40 NOP instructions along with the payload and rest of the B's. So let's just use this payload on port 110 as we saw on the Windows 7 machine. This we do not need to open a netcat listener on port 1337, as this exploit automatically spawns a netcat shell on this port once it gets a connection. So let's start. So once I launch the exploit, we should be getting a reverse shell of the Windows 7 machine on which the SLMail server is hosted on port 110. As you can see, the payload is being sent, and as soon as we launch this exploit, we get a reverse shell of the Windows 7 machine, and the exploit leverages the buffer overflow vulnerability of SLMail version 5.5.0. So we can confirm it is the Windows 7 machine by checking the IP using the IP config command. And once we see that, we can confirm that we have got a reverse shell of the Windows 7 machine, which is of the IP 192.168.131. So this concludes the webinar which we had hosted to explained the buffer overflow vulnerability at a beginner level, and also we also showed you two different executables that can be leveraged using this vulnerability. Thank you.